Today we're going to start standard 13, which is square root functions. Before we go into what the graphs look like, let's just remind ourselves what a square root function looks like. This is the parent graph for a square root, and we've seen this square root come up on quite a few occasions, especially with our previous standard where we have to square root both sides. Now, if I'm solving an equation like something like this, I might square root both sides, and then I have to remember to put a plus or minus when I solve this. However, when I have a square root function that just looks like this, where the square root is already given to you, we're just going to assume that we're always going to get a positive value. So this square root function, when we square root, is always going to give us positive, whereas when we solve, we can have a positive value and a negative value. So that's something we want to remember when we're graphing square roots. Before we go into that first graph, I just want you to go back into your prior knowledge, and I want you to take a few minutes to fill out this one. So take a few minutes, pause this video, and fill in what you think is going to be happening for g of x on the top and the bottom to describe that transformation. So now I'm going to go straight into this graph. So we've already graphed x squared on multiple occasions. Q of x equals x squared. And this is the parent quadratic graph. So if I don't remember what that graph looks like, I can always use my table to get these values and plug it straight in. So I'm going to end up with, 7 points that we have here so that I can graph. So a -3, 9, -2, 4, 1, 1, 0, 0, 1, 1, 2, 4, and +3, 9. Cool. So there's our quadratic graph, Q of x, the parent quadratic graph. So it's helpful to know how to graph the quadratic because it will help us with the values that we need for our square root graph, R of x. So let's start plugging it in the same way we did with the square root of -1. However, if I square root -1, if I remember from the complex numbers unit, I'm going to get I. But if we look at our graph, this is a real number plane. We do not have any i's, so this is actually undefined for the axis we're working with. But I can continue to fill in the rest. I could square root 0, 1, 4, and etc. And again, we're assuming this square root is going to give me only positive values. So I'm just putting 0, 1, 2, 3, and 4, as opposed to plus or minus 1 or plus or minus 2, etc. So now I have some other points I can graph as well for this one. So 0, 0, 1, 1, 4, 2, and 9, 3. And then 16, 4 won't fit, but it'll give me an idea as to where the graph is going to go for the rest of the graph. Cool. So we have Q of x and we have R of x. It also is telling me here that I want to graph y equals x as a dashed line. So y equals x is this little diagonal line here that looks like this. All right, so we have our parent quadratic, and now we also have our parent square root function. Let's identify the domain and range for each of them. So the domain for Q of x, so when we're talking about domain, we're talking about left and right. The furthest the left that it goes, it keeps going left forever, so that's -infinity, and right forever, so that is +infinity. When I'm talking about range, that is up and down. So the lowest that my graph goes is at 0, and there is a point there, so it's going to be equal to 0. And then it looks like it keeps going up forever to infinity. So when I write it in interval notation, because it's equal, I need to put a bracket. For x-intercepts and y-intercepts, it looks like there is one x-intercept that also happens to be the y-intercept at the origin, which is 0, 0. And there is no asymptote for these types of graphs. Then we have our square root function. So again, domain is left and right. So the furthest that my graph goes to the left is 0. And there is actually a point there, so it's going to be equal. And then it looks like it keeps going to the right forever to infinity. So my domain is from 0 to infinity. And it is a bracket because there is actually a point there. The range, again, is up and down. And again, the lowest point that it has is also at 0. And then it keeps going up forever. So it also goes up to infinity. So for this graph, this particular parent graph, the domain and range happen to be the same. However, if it was horizontally translated a certain way or vertically translated a certain way, then the domain and range might not be the same. But the x-intercept and y-intercept happen to be the same as our quadratic at 0, 0 as well. And again, also no asymptote. What do you notice about the graphs? So if I actually focus my attention on one part of the graph, there is something that I do notice. If I look at only this quadrant, and what I see is there's a reflection happening. When I zoom in, I see that Q of X and R of X looks like they're being reflected in this particular quadrant. However, we don't see a certain part of the graph that's reflected. This part is not reflected. So now that we've zoomed in on that, let's write what we noticed. So let's say in quadrant 1, they are reflected. Q of X and R of X are reflected over y equals X in quadrant 1. What do you notice about the shape of the square root graph compared to the quadratic graph? Well, the square root graph is only half of the quadratic. The square root graph is only half of the quadratic. Why do you think that is? Well, let's go and look at our table. Why is it? Why do we only get half for the square root, whereas for the quadratic we get a full piece? So if we look at the table, the quadratic, I'm able to square negatives and positives. Whereas if I look at my square root, the only ones where I'm able to get values is positive values. So the reason why the square root only gives us half is because we can only square root positives or non-negatives, whereas for the square, we can square any number. So let's say, we can only square root non-negative numbers.